There's a party tonight, right? I'm not going. I have to leave for Sweden tomorrow, so I need to get packed and stuff like that. Think about what to say there. So, an early night for me. Ah, 4:14. Should we do it? Nobody cares about what you say in the first 5 minutes anyway, right? Okay, easy asynchrony in C#. No more callbacks. So this is about, and I apologize if you've seen this all before, but this is sort of a back to basics, explain the core of how we let you deal with asynchronous programming in C#, starting with C#5, and how that works out with the .NET Framework 4.5, and in particular with the new Windows Runtime libraries, which you will be using extensively if you're writing Windows Store apps. So let's get that whole picture painted. And I'll spend most of my time in code, but of course there have to be slides because they give you a slide template. So I will say a little bit of stuff up front about this. So, just for quick context, nowadays everything comes with latency because it happens on a server somewhere and you're just sort of talking to it from the client app that a user is sitting with. So there's always latency in today's apps. At the same time, you have increasing demands on UI. You're not satisfied anymore with this sort of single point-and-click interaction. You want to be responsive to touch and all kinds of things. You want your device to feel alive. You want that surface to be smooth and fluid and all those words we come up with to talk about it. And so there are really high demands on responsiveness at the same time as the stuff you're talking to is taking longer to get back to you. Okay. So this is where the demand for asynchrony comes from. You simply cannot hold back the world, stop the world for a while you wait for that phone call from some web service or whatever to get a result back to you. You have to keep on running, keep on responding while you're doing stuff, while you're talking to the outside world and doing other things that take time, while you're experiencing the effect of latency. Okay? So that means you can no longer be synchronous. You can no longer do one thing at a time. You kind of have to be, in order to be responsive, you have to be asynchronous and deal with things out of sync, so to speak. So asynchronous programming as a programming technique is becoming the norm, and we are forcing you actually to do things asynchronously by only offering you asynchronous versions of APIs. So if you look at the Windows Runtime, I think about 15% of the APIs in there, and pretty much all the important ones are asynchronous, and you just don't have the option of waiting around for stuff. You have to do them asynchronously. So that puts pressure on you because you have to deal with this more complicated manner of programming. You can't just do your usual imperative synchronous thing anymore. On the other hand, we have better techniques to deal with asynchrony than we used to. In particular, we have new patterns in both the Windows Runtime, the .NET Framework, that are better abstractions for asynchrony than we've ever had before. I think we're on our third or fourth official pattern in .NET now, but so it takes a few shots before you get it right. But now we really have it right, and we have some powerful abstractions in the tradition of what's classically be called futures. Some people know them as promises. We call them tasks in .NET. Windows Runtime calls them async operations and stuff like that. They have different names. The main philosophy here is we have abstractions we have objects representing ongoing activity. So you have an object you can talk to about a given activity that it represents that is ongoing, from which you can eventually get the result, to which you can sign up callbacks to be notified when there's a result, and so on. So these first-class objects representing activities, that is the core of modern asynchronous programming. You can call that future-based programming, task-based, promise-based, depending on your philosophy. But that is the abstraction that you want to hold on to if you want to understand asynchronous programming. Okay? We all do it. We have different abstractions for it, but they're really the same at the core. They just have different names. Okay? So just to quickly outline the difference between doing something synchronously and asynchronously, let's say that we download some data and we now need to do something with it afterwards. If we do it synchronously, well, the code looks like you see up there. If you think of what happens on the thread, you do a little bit of work to kick it off. Your thread is blocked until you get stuff back, and then you can process it. Nothing else happens on your thread meanwhile. So this is what's bad if it's on a UI thread, or if you're running out of threads. If threads are the bottleneck of your application, and you kind of want to use them as efficiently as possible. It's not a very efficient use of a thread to have it not do any useful work, but just stare down a pipe waiting for the phone call. Okay? So that's why you want asynchronous programming. This is what future-based asynchronous programming looks like. You call an asynchronous method to kick off the download. You immediately get a ticket, a handle, a future, a promise, whatever you want to call it. That is the thing you will eventually get the result from. And then you can walk up to that and say, when you're done, please do this. Please take this code and please do something with the result. So you give it a callback. Okay? That means you're free to do other things as soon as you kicked it off. And then eventually, so on the thread here, you kick it off, takes a little while, you give it a callback. You can do other stuff. And eventually, that callback will get scheduled. You take up the thread's time a little more. Then you're done. And in the meantime, other stuff can happen. Like if you're on a UI thread, UI events can happen. It can listen to your mouse moving and blink things and whatever you're doing in UI. Whereas if you were in the synchronous situation, you all know this feeling of UI events either disappearing or catching up. Like you hit event enter 3 times because it didn't respond, and all of a sudden, it says your password was wrong because you hit enter in the password box that you were waiting for to show up or whatever, right? So events sort of either queue up or disappear. If you think about parallelism as well, let's say I want to do 2 things. I want to download 2 things, process 2 things. In the synchronous world, I have to do them one at a time. If I want to do it on this thread. In an asynchronous world, I can kick off 2 things, and I can sort of multiplex on the same thread here, right? I can kick off 2 things right after each other, and they can come back on my thread when they finish. So I'm sharing the thread. I have a shorter time to last byte. So all kinds of good things come out of asynchronous programming. Of course, the problem then is that it's really hard to do. So even with tasks and so on, and nice library support, it's a little cumbersome to do. And so in C# and Visual Basic, we've added language features to take the rest of the cumbersomeness out of it, to take the callbacks out of it, essentially. So that's what I'm going to show you. This here, the callback. That's the culprit. That's the thing we want to get rid of you ever having to write again. Okay? Even though lambdas are nice, we want to get rid of them from this particular scenario. So I'm going to switch over, press button 7, which is falling off when you do it. Wow. I can never press button 7 again. Pressed it too hard. And now what you see is a blank screen. Ah, there we go. So into code. I have an app. It's not finished yet. I'm going to finish it here. Let's see what it does so far by running it in the debugger. Hope I'm running it in the debugger. Yes, I am. It's a nice little Windows Store app. It's not very fancy. The idea here is that I want to build mosaics, these nice pictures that are made out of other pictures. That's what I want to end up doing. I'm not doing it yet. I have different categories of pictures here. When I click one, the intention is for it to go to Flickr, download 100 images or something like that with that theme, with that tag. Come back, ask me for a photo I want to have mosaiced, or whatever you call it, turned into a mosaic. Use those downloaded images as tiles and produce something that looks like my original image. Okay? It doesn't do that yet. As you can see, it just says done, which it isn't. So we have to finish it. Okay, and that's where we can get to explore a lot of the different asynchrony in the system. The asynchrony of talking to the Flickr service, the asynchrony of working with files, and so on. And let's start out just from looking at the anatomy of this app here. I have a split page. This is the page that I'm showing you, and I have exactly one event handler in here that's interesting, which is the one that gets fired when I click on one of these items here. Inside, I want to eventually, I have a little model behind that. That's sort of the structure of the thing, and when I update it, my UI nicely updates. I want to download some tiles. I want the user to choose a source image, and I want to calculate the mosaic and show it. Okay, so let's start from the top here and see what we can do. So we have a nice a nice Vue API for talking to HTTP. It's called an HTTP client, and it's really much better than the previous ones we had. So I think this one we also finally got right. And we want to get some stuff from the web. So let's look at get methods here. And what you'll notice is that they all, except for get hashcode and get type, which are probably about something else, they all end in the suffix async. So this is one of those things where you can only do things asynchronously. We don't let you do things synchronously. If you want to get something, you get it asynchronously. Too bad. So let's just take the general get method here. Why do we do that? Why don't we give you the synchronous option? It is to make it really hard for you to block your UI, because then your app will freeze and people will get mad and they'll think it's Windows' fault, right? And they'll blame us. So you don't get to do that. I'll show you in a minute how you can still block it and get us that way. But no, the intention, of course, is for you to have a smooth experience and go down the path of success. And this you will if you don't have an option for failure. So get async, you give it a URI. Let's give it a URI. I actually have a little, I'm not building this up entirely from scratch. I have some helper methods. On a Flickr tile provider here, I have something to get me a URI that I can send to Flickr based on the tag that was on the thing you clicked on, right? So it has, in the model here that we're looking at, it has a title, which is, birds or koalas or whatever. So given that, I construct the URI in my helper method, I pass it to getAsync, and then I get something back. Okay, what do I get back? Let's have a look here. So the signature of this method, called getAsync, this follows a pattern that we call the task-based asynchronous pattern in .NET because it uses tasks. The anatomy of it is it's called async as a suffix, so you know that it's async, and it returns a task or task of something. The task is a placeholder. It's that future thing. It's the ticket that you immediately return to the caller so that they can eventually get the result. Here we return a task of HTTP response message because the eventual result, once this completes, will be an HTTP response message. Okay? I don't have that response message just yet, but here is a ticket for it. Here's your sort of token that eventually you can use that to get at the result. So instead of previous patterns you may have seen where you have to first call to start things, then call to end things or whatever, it's just one call, you get the token back, you can do whatever you want with it, whenever you want with it. And it's a totally solid thing. The task, you can bang on it whichever way you like, and it doesn't break, it doesn't fall over and die after a certain amount of time or whatever. It's just an object you can always interact with as many times and in whichever way you want. So let's see what we can do with it. Well, eventually, I do want to get the result, and it has this very tempting method here called result, or actually, it's even a property. So that's probably fine to call, right? You should think about what happens if I call it. I'm going to do it anyway, but the thing that happens is it's actually going to block until the result is there. So I got the task async. I started out high style. I kicked it off. I got an async handle back, but then I immediately block on it. Let's just see what it looks like. I do get the result out, right? So I could take it and keep going. Var response equals that thing. But let's see what you can kind of guess what the experience will look like here. But just to bring it home, let's click on these birds and then move the mouse around. And what you see is my UI is not responsive for that second or so it takes. I have fast internet here apparently, so it doesn't take that long. But for that second it takes to talk to the Flickr service, I'm not responsive. See, I'm not responsive, then I'm responsive because it's blocking the UI thread. Okay, this is what we don't want. So synchronous is bad, and now we've seen why. So the question is, what can we do instead? Well, the thing, without language support, the thing we have to do is to sign up a callback. And the way you do that on a task is continue with. The continue with method lets you sign up a callback. So this is where I have to get into, my God, there are 40 overloads of, so even figuring out which one to pick. But the first one looks pretty good, so let's go with that. We give it an action, okay? So it's an action that the completed task, you get it in here again for completeness. You take the task after it completed, gets passed to the callback, so we can grab stuff out of it. And now that means that, well, I guess all the work that happens after here, that's sort of following, we kind of have to do that in the callback, right? So we wrap all this subsequent code in the callback and pass that to continue with, and we want to somehow get the response out of it down here equals, and now we can walk up to t.result because now we know that it's complete, so it's not going to block. Let's remove this. Hang on. Fat fingers. So now we sign up callback. It's supposed to run after the thing is complete and get the result out and print those things on the screen. Let's see if it runs. Oh, I gave it away. Let's see it run. Okay, we'll click, and we should now see it be responsive. And it's responsive. Yay! Whoa, but I get an exception. Okay. So now we have two questions. Why do we get an exception? Is one. And the other is, why didn't we catch the exception? Because we had a catch block before. Okay. So let's look at the second question first. Why didn't we catch this exception? Whatever it was. Oh, hang on. Let's get out of the debugger here. Well, if you look at, see, I'm even in a different piece of code here. The exception just totally went somewhere else. Okay. So why was that? Well, I have a nice try block to try catch wrapping my whole logic here. So lexically, it looks like I should catch all exceptions. But the problem is, yes, it may be lexically enclosing, but it's not enclosing in time span, right? Because when I run this event handler here, the last thing I do is call continue with, passing it some callback that may run in the future. Then I exit out of my catch block, out of my event handler, back to the UI thread to party, okay? And I'm not out of my catch block. So the catch doesn't apply to what happens in the callback, which means I have to do my own error handling on the callback again. So maybe I could like put another try block here, and I can reuse my code in the old-fashioned way, copy paste. So let's go do that. Where do I want to put that in? Probably here, right? Something like this. Let's get it nicely indented at least. So now I should be good. Just to be sure we know what's going on, let's put a breakpoint here, breakpoint there, breakpoint, breakpoint, breakpoint everywhere. Run the thing again, and we still don't know what the exception is, but now we see that when we get the exception, we actually get into the catch block. Okay. So I have to repeat my exception. I have to somehow replicate my exception handling at every level of callback. So now we should be able, since we swallowed the exception, we should be able to continue here. Whoa, no, we get another exception. So now we have to kind of have to look at what is the exception. I don't know why it's not showing the exception right now, but it should be. What the exception says, if we look at it, I really wanted the exception to show here. Let's try again. First we get here, then we continue running. Here we are. Here we get the exception. What it says, and you may not be able to read that, doesn't matter. The application called an interface that was marshaled for a different thread. Okay. Now, if you've seen this before, you know that what you did was you did UI operations on a thread that wasn't the UI thread, and you can't do that. Why did we do that then? Well, I'm continuing to press the wrong buttons here. I apologize for any dizziness. Why weren't the UI operations called on the UI thread? Well, that's because maybe the callback wasn't run on the UI thread. We started out on the UI thread for the event handler, but the callback wasn't run on the UI thread. So when we did model.statustext equals something, that throws an exception saying you can't update the UI from here because I'm somewhere else. And that's why we get the exception again when we go into here, because we handle the exception by updating the UI again, which we still can't do because we're still on another thread. Okay, so we have to get back on the UI thread. Why aren't we? Where are we? Well, continue with probably, you know, what woke us up in the first place? Like what caused the callback to fire? Well, probably some I/O completion thread got the result back from the web, and it said, oh, I have some callbacks here, doom, go call those, on that random IO completion thread somewhere else, and that's the one that's running us. So we don't want to be there. We don't like being on this thread. We want to be on our thread. So let's go put ourselves on our thread. So there are various ways we can do that. There's a dispatcher object here that you can run on. Well, you can run async on it. Okay, fine. And you can pass it, well, we need to give it a priority. I don't know why, but let's give it one. What do you think? High, low, normal? I don't know. I never know. Let's grab one. And then we give it a callback, which is run this stuff on the UI thread whenever you have the time. When you're ready, in your own time. Post this on the UI thread. And let's see, we probably put a curly here, end it there. Does this look right? I think it's right. Okay, so now we can run. Now we've managed to handle, yes, done. Yes, done comes from the callback. Okay, so now we managed to handle one asynchronous call, getting a result back from that. We have in our code, I just want you to observe, we have now 3 additional levels of nesting from the extra try handler, from the async callback, and the post back to UI thread callback. You can do better with libraries. You can make this a lot smoother. If you do promise-based programming in JavaScript, you may know this. C++ also now has a nice library like Task that makes it a little better. But you still have to, so you can chain things and not nest them so much. But you still have to do special things for error handling. You can't do things inside of a loop or anything like that. So your whole normal code structuring sense is busted. Right? This is the long speech to motivate this thing. So we don't want to do any of this. We want our language to help us out. And that's where async comes in, right? So let's get back to where we were with the HTTP client until we got before we got the result here. Here where we get the task. What we can do with that instead, let's go and look at what it actually says we can do. It's been saying it all along. This thing is awaitable. When you get a task back, it's awaitable. What does it mean how do I await something? Well, you say await something. It says usage. Read that manual, okay? Okay, let's await it. Wait. I get an error. Why is that? We really help you out here. The await operator can only be used within an async method. Consider marking this method with the async modifier, changing its return type to task. Okay, let's just forget about the return type for now and mark it with the async modifier. And what you see now is the await keyword lights up down here. So apparently I could do this. Okay, and if we go look, now, for now, this is magic, but what you see is await has the await expression, the whole expression there, has the type of HTTP response message. So task comes into the await, response message comes out. It converts, somehow it gets me the result. Great, so let me grab it while that's still true. Var response equals, okay, I'm going to run it even though I haven't told you how this all works, or if it all works. It does work. I've told you that now, but I haven't told you how. So let's run it. I am responsive, and then it comes. So it works. It does the right thing. How does it do the right thing? That's what we're going to talk about a little now. The await keyword, which can only be in async methods, is essentially doing everything I did manually just before. That's why I took you through the exercise. It was not just so you could see it was painful. It's so that you have a basis for understanding what really goes on behind the scenes with the await keyword. The await keyword takes a task or something awaitable. There can be other awaitable things, which we'll see in a moment. Signs up a callback to that task, and then returns out of this method. We're done with this method. Returns out. Okay. So once we get to the await keyword here, we're out of the event handler. But we signed up a callback first. So that's kind of like with continue with before. Right? Sign up a callback, get out of there. What that callback does is first it gets us back on the right thread. Okay, back on the UI thread where we were before. So once the task completes, the callback gets that the compiler signed up, fires, puts us back on the right thread, and then parachutes us on the right thread right back into the code right here. Okay, so it gets you back to where you were in your code. So you don't even have to think about it in a callback-based fashion. All you can think of is, when I get here, I get off my thread until I suspend the execution of this, get off my thread, let other things happen on that thread until that task is complete, at which point I get resumed on my thread right where I left off, which is just as I was about to get that response. So now it comes out. I'm back in business. I'm running the rest of my code. Okay? That's how it works. Now, it takes a lot of compiler munging, similar to what maybe you know from iterators. If you look at all that stuff in Reflector or something, you will see very horrible code in there. But that's the point, right? We write the horrible code for you. You don't have to write it. So if you remember nothing else, remember that this is what await does. Takes an awaitable, signs you up so that you get off the thread, you get resumed when the callback is done, or when the task is done. Okay? So you can use your thread for other things. Now, the rest of this talk is just refinement of this. This is the main message. Good. So now, I mean, one refinement is we actually want to get this app to work. But let's learn something along the way. So now we have a response. Let's go look what you can do with a response. I love this exploratory kind of programming. You just dodge away. Well, it's pretty content. I like that. We got to read something. You can see I practiced before, so it has all the right things highlighted to begin with. I probably want a string, because I know I'm going to get some XML. So I'm going to read it as a string. This is async. What do you do with async things? Yes, we await them. Well, not here. I didn't click here. So awaited. What do I get out? I get a string. We know it's going to be some XML, so we just do this. So it's kind of like you're programming just like before. Sequential programming. It's one statement at a time. Exception handler around it. Deals with all exceptions. You could have loops, awaits in them as well. It's all the same stuff as you're used to, except once in a while you have to say wait. No big deal. So this is going to sign up another callback on this one, as we're already running in the callback from the first one. So callback, signing up, callbacks, until we're done. It's just a big change, no problem. It's just, you don't have to think about that. You don't have to wire it together in your head. Okay? So now we have some XML. Let's get the best out of that. And I actually have some more helper methods, because you don't want to watch me just program. So the Flickr tile provider has parse photos from XML. That's good. I have some XML to parse photos from. And it's not even async, so I can just say var photos. This is pretty lame, right? This is just straight. I got some photos. That's actually, what are the photos? It's a list of photo infos. I don't have the actual photos yet. I just have a list of IDs for the photos I got back. So let's fetch the actual images. Let's call them tiles. Equals. I have another helper method for that. Flickr tile provider dot fetch images. Async. Ooh, async. It takes that list that I got before. So let's give it that. So photos. And I'm not going to, that's an optional argument. I'm going to ignore that for now. And this was async. So what do I do with it? Louder. Yes, I awaited. And now I have the actual tiles. Okay? So the idea is, if we go back to our logic here, we now have some tiles. We've got to still ask the user about it, but eventually we're going to do something with the tiles down here. And so the tiles, we have those tiles lined up. We need to get a source picture, and we're in the game. But before we do that, I want to talk a little bit. So now we have an asynchronous method here that's void. Nobody cares when this method completes. Okay, it's just an event handler. It's fire and forget. Nobody cares when it's really done. However, you saw me calling other methods, including helper methods I claim to have written myself. Actually, there's a guy on my team that did it. And they're task returning. So how do you write a task returning method? Well, the easiest way is to get Visual Studio to do it for you. So let's go and grab these 4 lines of code here and do a refactoring. We have plenty of refactorings in Visual Studio, and this is one of them. So let's get a method. Let's call it getTilesAsync, because obvious names are always good. And what happens is we factor out, you see down here, a getTilesAsync method that has all the stuff I had in there, but it's itself an asynchronous method, okay? Because it needs to await stuff, so it has the async modifier on it, because you need that. We saw that before. But it has that signature that you've seen before. First of all, it's called async by convention, because I named it that. But also, it returns a task of the kind of result we eventually want to get out once this asynchronous operation completes. Not when it returns, but when it completes. Okay. When it returns, it gives the caller, which is me up there, up beyond where you can't see it. It gives the caller this task. There's a ticket for a future thing. So our job inside of this method is to do the work and somehow create that task, send it back first, then do the work, then notify the task that it's done. And that's, again, a little annoying to do. So when you have an async method that doesn't return void but returns task, then the compiler will do that for you too. Not only will it do the await, but it'll also do that thing. So it'll create a task, return it to the caller as soon as you hit the first await. So when you return from the first await, that task goes back to the original caller. Then you get resumed more times every time you hit an await along the lines. And eventually you get to the return statement. Well, the return statement does not return to the original caller, because it can't, because we already did that when we returned that task. So what return sort of is reinterpreted to mean in async methods is, this is the result. Produce this result. So instead of returning, because there's nowhere to return, what it does is it goes up to that task that we returned before. It says, you are now complete. This is what your result was. So it can notify whoever's consuming it. For instance, it can notify me up in the other method when I'm awaiting it. Okay? I'm awaiting it up here, and I get the result back out of the task. So what you see is, it's easy to write asynchronous methods that produce results, and the sort of procedural composition you get, calling methods, you get that back just like with synchronous methods. You just have that little extra indirection layer of wrapping them in tasks when you produce them, awaiting them when you consume them. Okay? You got your procedural abstraction back as well. You should be really happy with this. Okay. So far so good. We have now thoroughly examined the task-based asynchrony here. But I told you that there were other kinds of asynchronous promises, futures, tasks, thingies. Okay? In particular, the Windows runtime that you code against when you do any UI things or file things or so on in a Windows Store app has its own concept of futures. Some are called async operations if they have result, or they're called async actions if they don't. The point is, it's a different type. It has a different interface. So let's go call one of those asynchronous operations and see what's different. Okay, so now we want to choose an image, and that's a typical UI thing. So we now go talk to the Windows runtime. First, we want ourselves a picker. So there's something called a file open picker, which is the UI you can call to ask the user to pick a file. You can't give it any arguments, but we do want to customize it a little bit. We want to say only certain types of files are interested in here. Let's get JPEG files. Let's get JPEG files with an E. Oh, that turned out wrong. That's because I forgot to put the curlies here. So .jpeg, .jpeg. Let's get the PNG as well. What's that? Thank you. What would I actually do without you? So, anything else that's wrong here? I'm not done, but that's the only thing. Okay. Cool. We can also choose a view mode. Let's just do that. Pick a view mode. I can either have a list, but thumbnails are nice because these are images. So let's do that. So now I have a picker that's set up in a certain way. Now we can go and pick something. So let's pick something. Picker dot pick. Multiple files async or single files async. You again see a pattern here. It's async. And what you see, it's awaitable, but the thing it returns is not a task, it's something else. But we don't care, it's awaitable. So let's do this. Let's actually go to definition here and see just briefly what we're looking at. So pick single file async returns an iasync operation of something. That's a Windows runtime type. That's fine. Let's look at that. And you can see it has a completed, instead of having continue with, it has a completed event which is an async operation completed handler, but it's sort of the same thing, just different. It also has a get results instead of result property, but it's similar, but different. Okay, so it's clearly capable of doing the same kind of job. The main thing, though, is that it's awaitable. Okay, why is it awaitable, actually? That's because everything that's awaitable follows a secret pattern. You can follow the same pattern. It's not secret, it's in the spec. But it's secret in the sense that the method you need to have does not show up on the, in the completion list. It has a method called getAwaiter, which, again, has some things on it. You can see it didn't show up in completion, but it's still there because we hide it from people. We don't want people to do it. We want them to actually await things. So there's a couple of things in there that the compiler uses to sign up completions, ask if it's complete, do things like that. There's an agreed-upon interface that everybody has. They offer a get async method. You can put it on as an extension method, so it doesn't have to be thought of in the original type. So anything that's future-like, you can make it awaitable. But I'm not going to tell you too much about how that works, other than it's there. It's pattern-based, so anything can light up with await. So it picks a file. We should get that file. Let's call it the original. And now we have a file. And we want to display the original file, and eventually we also want to display the result. So there's a little bit of stuff we have to do here. Bitmap. I'll do it quickly. We need a new bitmap. Bitmap image. We need to set a source for that. So bitmap dot set source. Actually, let's see. Bitmap dot set source and set source async. And the set source says you should probably use get source async or set source async. So let's do that. It's one of those places where apparently somebody couldn't live without the synchronous version, but we can because we are waiting. So let's just set source async. We need to give it something. Let's try to give it the original. It doesn't like that. It needs it to be open for read. So we'll do that. That's also async. So we need to await that as well. Await that. Now it's opened, but we also need to await this thing because that's also async. So now here we have two async operations in the same line. One returns something, a stream or whatever. So we await that to get that stream, pass it to the other async operation, which doesn't return anything, but it's still awaitable. So we await it just to wait until it's happened. And once we know it's happened, we know that this bitmap has the file as its source, so we can display it. So we can say model.original image equals that bitmap. Okay? And that should work. And it's about time that I run the app so that we can see that. I shouldn't go away because I need to click something. So we can see that it actually does the right thing. So now it'll go talk to Flickr. Then it will ask me for an image, a beautiful image. Let's get this one here. That it should then try to produce a mosaic of instead, if it wasn't for the fact that we hadn't done it yet. So far, so good. You've now seen task-based asynchrony, and you've seen Windows Runtime asynchrony, and it all just works together. So eventually, we can't avoid it any longer. We want to go and compute some actual mosaics here. Before we do, though, let's do one more interesting thing. What's that? Can I click a button that gets him back into the UI?
Because the UI is responsive, you keep doing this while you're out on those other tests, and then you have all those things popping up with the
Well, I'm not sure what the question is. So, can I keep clicking? Oh, yeah. You want me to see me keep clicking? Let's keep clicking. I click on this one, it goes. I click on this. Oh, I didn't have time to do it. So it's a little hard to get it in there, but yeah, I could. But I wonder what happens now. I click twice. Does it go back and do it again? No, apparently it doesn't. So yeah. So I think the core of your question really is, it's kind of silly that I click, and then I wait for a while, and then the picker comes up. Now, I could have done all sorts of crazy stuff in the meantime, including clicking more times. So that's not a good, it's not a good user experience, even though it's responsive. Like, what can I use that for, right? And so that's actually a great segue into the next thing I wanted to say. Because you kind of, if you think about it, downloading the images here, the tiles, and getting the image from the user here, those are independent operations. Like, they could happen at the same time. I could kick one off, then the other off, and have them happen at the same time, like simultaneously, just like in that image in my first slides. And tasks make this kind of thing depressingly easy, okay? Let's think about what happens here. So all I've done for now is whenever I get an awaitable thing, I immediately await it. I can't wait to await it. But maybe I should wait a little, right? What if I grab that task? I just told you before, you can do anything with tasks anytime. So let's just hold it for a bit. Let's just grab that task. We kick off the operation. We start downloading. But then we don't wait for it to finish. We just keep going. Because we have the UI thread. So we do it there. And when do we actually need those tiles? When we only need them down here. So maybe we don't wait until we actually need them. Okay? And then we get the tiles. Okay? Thank you. So that's kind of cool, because I kick something off, and I leave it there, but I have a handle to it. I do something else. That thing is happening out there somewhere, but it's mostly happening by nothing happening on my machine, but some traffic going on the interwebs, right? And then, you know, either when I get to this line here, this await here, either this task is done or it's not. Okay? One of them completed first. Like, either my path through the main method here completed first, or the other task completed first. One or the other. Whatever, you know, whenever they do something, they do it by posting a little, you know, they have all these awaits that they spend most of the time doing nothing, being suspended. But whenever they do a little bit of work, they come to the UI thread and do it, and then they're off again. So they kind of just interleave, poke little bits of work on the UI thread, and it has plenty of time to also respond to your work as the user poking things in there. So they just share, time share, and one of them will complete at some point. But no other threads were harmed in this process, right? It all just happens with little bits of work happening on the UI thread. When we get here, if we got things downloaded before my fat fingers picked a file there, then awaiting it will just immediately produce a result. No callbacks, no nothing, because it's already, the task is already complete in the meantime. I just grab the result tab. Fine. Okay. If it wasn't done, well, we sign up a callback and wait for it. And then we're done. No big deal. Awaiting something that's already complete, no big deal. Awaiting things twice, no big deal. What about side effects? That's a very, very good question. So let's talk about that just a little bit. The whole point of asynchrony is to let other things happen during those awaits. It's to let other things run on the UI thread. That means that you can have side effects that one asynchronous method, side effects occur in one asynchronous method that are observable during the execution of another. So the usual thing you have on the UI thread, which is, I own it till I'm done. You don't have that anymore. Okay? That's, maybe I'm not getting your question right, but let me answer the one I thought I got, and then I'll return to what it actually was. You don't have that anymore, because the whole point of await on the UI thread is to let other things happen. So those other things can be nasty to you, and then can change some state that you depended on. You don't have an automatic lock on state anymore. You have what's more similar to, what's it called? Collaborative scheduling, right? You have certain points in your code where you let go of the thread and let other things happen. And they could mess up whatever assumptions you had about the global state of things. The model object could have changed, whatever. Okay? So you have to be prepared for that. You have to sort of think about new things. It's not exactly concurrency, because you can't have shared state updated at any arbitrary point in time, but any shared state, and UIs have lots of shared state. The whole UI is shared state. Can change during awaits, because you're letting other people muck. So that's something to be aware of. As my colleague Alex says, with great responsiveness comes great responsibility. So it means you now have to be prepared. You can have multiple things happen at once. Yay! Now you need to be prepared for multiple things happening at once. What was the actual question? Sorry.
I think that does answer the question, but let's do a little scenario. So let's say that conceptually you're limited. I'm just making this up. Let's say you're limited the number of requests you can make to Flickr. So down in that asynchronous method, get tiles async. You implement a count down in the. You have to scroll down to see it.
Oh, okay. Yeah. Yep.
Let's say that modifies an object, an instance level variable.
Yes.
And ticks a counter.
Yes.
So you're keeping track of that.
Yes.
This UI thread really can't touch or observe that counter from the time from the time you call get tiles async until you have completed awaiting the var dummy await tile task.
It can actually observe that state because the state, if the state is shared instance level, then that state, if it gets modified in one part, it can get observed by another part of the code running. It's no magical hiding of it. So that's part of that issue.
Right, but multiple threads could be modifying that counter.
Yeah. Yeah, you can't. What's that? They can't hear him. Let's take the details offline. So I think I gave the main idea here, which is things can happen to global state, and you have to worry about them a little bit, but probably not too much. I'm gonna zoom out of demo mode here for a little bit, even though we haven't actually computed anything yet. That's going to be the easiest part. And just to quickly summarize, because the talk is almost over. Async, to make your method asynchronous. Await turns the rest of your method into a callback, sort of. Suspends, resumes when you have the result. Fine. We've seen two different kinds of awaitables, the tasks in .NET, the async actions and operations in Windows Runtime. They're pretty much the same. You get them from async methods in those APIs. You can await them directly. You can await them as many times as you want. You can store them and await them later. Additionally, if you want to get, there's additional stuff I'll show you in a minute that you can do with tasks. If you want to get a task and do that additional stuff with something from the Windows Runtime, you just call the extension method as task, and you get it as a task instead, and you can do that stuff. So it just wraps it. Okay? So also we've seen avoid returning async method. That was the event handler. It's fire and forget, right? It doesn't return you anything that you can wait on to know when it's complete. Or you can have task returning async methods that will produce a task that you can then wait on. So you use those for any helper methods like we had or for libraries. The other things are more for event handlers and that kind of stuff where you just want to kick something off and nobody cares when it's done. Okay? Next demo. So we're almost done here. I just want to say a little bit about coordinating tasks here, because now we're going to go move away from our silly little dummy here and actually do some computing. So what we have is another helper method that I already wrote. That's called, so we have a mosaic builder type, and it has a create mosaic. And you totally don't notice right now that there's also an async version of it. I'm going to call the synchronous version of it. So we give it the original store file here. We give it the tiles, which remember we have to await. Tiles task, because we're only just now waiting for the completion of them. So now we're creating a mosaic. Thank you. I am really bad at this. How did I ever get into C# in the first place? So I create that mosaic. I get mosaic back. Okay, that's another storage file. And I'm good to go, right? And then I can do something with that. Actually, let's finish the code here. I want to do the same thing again where I get it into a bitmap. So let's extract a method for that so that I can display it, right? So get bitmap async. So now we have a get bitmap async method that we can call again here. Let's just say model dot mosaic image equals await get. You get the idea by now, and then use the mosaic file instead of the original file here, and we should be done. Okay, so let's run it. And you can sort of anticipate what will happen now. Okay, so now I call this big method to compute. Oh, you notice, by the way, I didn't have wait time anymore when I clicked because it's downloading in parallel. I didn't show that before. So now, unfortunately, I'm unresponsive again because there are other ways you can block the UI thread than block waiting for something. You can also do a lot of work on it so you don't return for a long time to the message pump and don't let it pump. And that's exactly what happened here. Now you see I have my first mosaic here. Isn't that beautiful? And now I'm responsive again, but in the meantime I wasn't. So let's just imagine for a second that create async is a really hard computational thing that really shouldn't happen on the UI thread. Well, the old wisdom is take all that hard work, put it on a worker thread. Don't waste cycles on the UI thread on it. However, that just got a lot easier. So all the marshalling and all that other stuff that you had to do before, you don't have to do that anymore. So let me show you how. Task, the non-generic task, has a bunch of static methods on it that are helper methods that we'll explore in this segment. One is task.run. And what that does is it takes a lambda and queues it up on the thread pool, runs it there. Okay? So let's give it a piece of work to do, which is this create mosaic piece of work here. Now it complains that I'm not in an async method. And that's true because the lambda I'm in is not async. Okay? So we've got to make it async. And this is just to show you that you can also have async lambdas, and that's just fine. Okay? Thank you. So it's going to do some awaiting over on a thread pool thread somewhere as well. That's cool. That's fine. You can post asynchronous work to a thread pool. When is it done, though? Well, task.run returns us a task. That'll tell us when it's done. So we can await it. Look at that. It returns a task of storage file, which is exactly the thing we want. So we just await it. So now what's happening is we now run that work on a helper thread instead of on the UI thread. We just had to wrap it in a little call to do that, in a little lambda, and then await it. And now the UI thread is free while this work is going on to do other stuff and get signaled, just like with all the other asynchronous methods, get signaled when this work is done. So the only difference here is we're doing CPU-bound heavy lifting work on another thread instead of doing communication-heavy work with the internet or something. Okay? Same deal, same abstractions. This is how you offload work from a thread to another thread. Task.run, await the result, off you go. So now it's responsive. Maybe I shouldn't show it. Takes a while. Exceptions. I haven't talked much about exceptions. I probably should. So now you'll see it's responsive again. Okay, we can't be bothered to wait for it to actually complete, but it's responsive. So I should say something quickly about exceptions. I said the tasks are kind of a wrapper for the result. Okay, a place where you can eventually get the result. It's actually more abstractly the outcome of a method. So if an asynchronous method terminates with a result, then the task will complete with that result. If it terminates with an expression or with an exception in an exceptional state, then the task will actually capture that exception and contain that exception. And when you await a task that represents something that ended in the wrong way, in an exceptional way, when you await that, instead of the result coming out, because you don't have one, the exception comes back out. So that's why exception handling actually works here, is because when I await something, let's say an exception comes out of task.run, I'll catch it here because I await it, and await will release that exception. So if an exception comes out of the work that's on the worker thread, the task.run will make sure that exception gets back to me. So one of the really hard things about marshalling work to another thread is dealing with the exceptions, or used to be dealing with the exceptions. Now it's easy. You just await it, and results or exceptions, whatever, come back to you. We don't have time for the rest of the presentation if we take questions. So is it OK if I finish, and then maybe we can take questions offline? I'm sorry, because I love questions. And the exception one was really something I forgot to say. Now, there are a few, because I do want to show a few more of the helper methods and task.run. One thing you did notice was that, yes, now it was responsive, but it still takes a long time to compute. And we may want to tell the user, hey, we're still working. We're not hung or something like that. So one thing I also want to show you is that we can race tasks against each other. And I'll use that for printing a notification to the user. So let's say that we grab, again, we do the same trick of grabbing the task here for the mosaic, but not immediately awaiting it. So this is going to take a while. Now we create another task. Immediately after we kick that work off, we create a task representing a 4-second delay, say. So there's a task.delay method, which will produce a task that will complete in 4 seconds. So now we have a race. One thing will complete first. How do we know which completes first? Well, we can ask. There's another helper method called task.whenAny, which you can give it a bunch of tasks, and it will immediately return a task that will complete when any of those tasks complete. Okay? There's also whenAll that will only give you a task that will only complete when they're all complete. But we want whenAny for this, so we're going to race these two against each other, the mosaic task and the delay task. Okay? Now, what do we get back? We get a task of tasks. Okay, that's a little weird, but let's try awaiting it and see what we then get back. Now we get a task back. Let's await. No, okay. No, await here. What it gives you back is it immediately gives you a task that when it completes, it tells you which of the tasks completed. Okay, so we'll grab that task, var completed task. So now we know which one completed. Now we can ask. Compelled it? Okay, never mind. As long as I keep it consistent. If the compelled task was the delay task, I'm just doing a reference comparison here. If the task that completed first was the delay task, that means 4 seconds elapsed, and we're still not done computing. Then we can do some stuff. Let's just say model.status text equals still computing. And this will only happen if it takes more than 5 seconds. And then because I turned the mosaic because I just kept the task instead of completing it, then we have to await it down here. Now, if I'm lucky, you should see this behavior live. I click here, I click here, I click here. Now it's calculating 1, 2, 3, 4. And it printed out the message, right? Because it took longer than 4 seconds. But if it hadn't, then it would never have printed that, because that wouldn't have been the one that won the race. Okay? So just to show you some of these coordination things. The final thing I should mention, and we have 4 minutes left, so I'm just going to skip the slides and do it right here, this sort of concludes the async part per se. But there are things you often want to do when you have long-running operations, and things are async because they're long-running. One of the things you often want to do with a long-running thing is you want to be able to cancel it, at least a nice cancel where you say, hey, I regret it I ever asked you, so I'm not going to ever depend on your result, so if it's all the same to you, just pack up and save whatever resources you can. Okay, that's a soft cancellation. And that's really useful in a resource-limited system, right? The other thing is you might want to get progress, like how far are you, how far are you, how far are you? So we have patterns for how asynchronous methods can offer the ability to be canceled, so cancelability, and how they can offer the ability to report progress. Okay, I'm going to show cancelability quickly here. So let's look at a random asynchronous method. You've seen some of these overloads or optional parameters a couple of times, and I've ignored them. Asynchronous methods can offer cancellation by optionally taking a cancellation token. Okay? A cancellation token is a little warning lamp that they can get that they can look at once in a while and say, whoops, it's blinking, I'm canceled. Okay? And let's make one of our helper methods down here cancelable quickly, the getTiles method here. So we can take an optional cancellation token here. Let's call it cancel, and just set it to a default value. Default of cancellation token. So the default cancellation token just never cancels. So that's a good default value if people don't pass it in. And then what you usually do is you call other asynchronous methods, and if you're lucky, they also take a cancellation token. So all you need to do is pass it on. And that's all you need to do. So whoever cancels you gets to cancel them as well. Okay? So if they're in the middle of doing their thing, they get canceled too. What happens if you cancel? The contract is, if I offer cancelability, I take one of these guys, and if I'm canceled, I throw an operation cancel exception back out. So that's sort of a tear down coming back out. So if this guy cancels, when we await him, we get one of these cancellation exceptions because he ended And that we'll pass that on. That'll get unwrapped and caught by our exception handler further up. Okay? And we can, if we don't, like this one doesn't have a cancellation token overload. If we're uncomfortable with that, we can cancel ourselves directly, saying throw if cancellation requested. And that'll just do the same thing, throw one of these operation cancel exceptions if somebody requested cancellation. And we can get out of doing the rest of our work and exit out of any finalies we have or whatever. Okay, so that's how you handle cancellation. How do you signal cancellation? You need the button to get the lamp to blink. That's called a cancellation token source. So you can get one of those. You can just create one. So var, let's call it myCTS equals new cancellation token source. And that's the kind of thing you can get them from. And then when you want to, so that's a button I can press to cancel. And then we want to pass it to, for instance, our asynchronous method here. We just say my cancellation token source dot token, and that gives us the lamp we can send them down. Okay, so I do that to all the asynchronous methods down here, but I won't because I don't have time. And then the last thing we need is we need to trigger the cancellation through this cancellation token source. So for instance, we can do that. What you typically want to do is you want to publish your cancellation token source to the object, so you can see what's the thing that's going on right now that deserves cancellation. So we could have a cancellation token source CTS out here that is just null normally, but when an operation runs, it will set that. So when I start my operation here, I'll publish to the world that I am now undergoing, and you can cancel me if you want to. So I do that by setting CTS equals my CTS here. And then when I'm done, I can then say, when I'm completely done here, I can say if the CTS is still mine, then I get to set it to null again, saying I'm done. Okay? But somebody else might have published something in the meantime. Then the way I can cancel it, for instance, let's just pretend that the back button is a cancel button here. I can then just simply decide that I use that to call the cancel method on the cancellation token. That sends the lamps blinking. That sets the operation cancel exceptions bubbling up from whatever is currently ongoing that's listening to this cancellation token. You get tear down. I wish I could show a little more, but I'm out of time. So going back, just to wrap up, this is the last session, so the doors are still locked. So just to back up quickly, tasks, we saw these different helper methods and tasks, and cancellation and progress you do by passing in objects, optional parameters that signal cancellation down or gather progress up. And that's the pattern that you use for that. The main thing, though, no more callbacks, use await for anything asynchronous, and you're a happy camper, and all these other things with task helper methods and all that, that's just sugar. That lets you coordinate, lets you parallelize, do fancier things with asynchrony, but even getting, just awaiting everything right away gets you responsiveness for free that you didn't have with synchronous programming without all the callbacks and all the goo. Okay, so that's really the message I wanted you to go away from here with. All right? Thank you.